let's visualize this a little bit further. So what we have in general, if you think about traditional or standard machine learning, usually on a very high level of abstraction, we have the following pipeline. So we have some raw data, for example, and we, for example, as machine learning researchers or as engineers, we think a lot about how can we extract useful features out of the data. For example, if you think about an image classification, how can we describe mathematically the edges that are contained in those images? And once we have such a compact representation or descriptions, or once we have derived those features, we'll usually feed them into a machine learning model, into a machine learning algorithm, not model, apologies. And this machine learning algorithm will then hopefully learn some kind of decision boundary or probabilistic model in order to classify the content of this image. So that's this traditional machine learning process. In comparison, what the main idea of deep learning is, we want to a certain extent, and I really want to emphasize to a certain extent, get rid of this human in the loop here. So we want to achieve the same task in a so-called end-to-end learning fashion, where we provide the model the raw data, and the model should preferably learn itself what are the relevant features that we want to extract from the data in order to, for example, accomplish a certain task like image classification, and that will be our solution. And if you think about this from an image perspective, and this is just to visualize it again, so for example, in the classical machine learning pipeline, what we have is, for example, an input image. We think about maybe some edge descriptors where, for example, here some gradient features are extracted from the image, and then we feed into our machine learning model these gradient features, and as a result, hopefully this model learns to classify this image or detect if there's a bird in the image or if there's no bird in the image. In a deep learning setup, this looks a little bit different. So what we have is, for example, we have an input image, and the deep learning model is learning over time with progress and training to extract features itself out of this image at different layers of abstraction. So for example, in the first couple of neural network layers, it learns these low-level features that correspond to the edges that we have, for example, also discovered based on our human intuition. And these edges are then, for example, composed to more complex structures in the preceding layers to form so-called high-level features that will then help us to accomplish the same task that we try to resolve as well in the machine learning approach. But ultimately, and this is actually empirically shown in many situations or many use cases already, with a much, much higher performance than with the traditional machine learning methods. So this is what we have here in deep learning. Does this make sense, or are there any questions? Can we have a look at the chat?
Sorry, to clarify, you mean there's higher performance in those empirical studies using traditional machine learning or using deep learning?
Using deep learning.
Okay, got it.
So this is like, for example, if you think about image classification, there was this, if you want to say, watershed momentum in image classification in terms of the so-called ImageNet challenge, where researchers, I think in 2014, really showed that using deep learning models, they had the chance to significantly outperform those handcrafted feature models.
Marco, I also have one question. So to better understand this manual feature extraction in the machine learning process, do you think this example makes sense? So the example is that if we want to predict fraud using financial statement data, right? So in the machine learning approach, the manual feature extraction could be that we use raw financial data to generate financial ratios, right? For example, the current asset versus current liability, right? We create those interpretable features and input that into a model. Whereas the deep learning can directly utilize the raw financial variables, right? And let the machine figure out what's the relationship among these variables. Does this example fit into the difference that you put here?
Yeah, absolutely. So thank you very much for the question. And I think this is a good one. So what we have usually, and I will show some examples later, is, for example, if you think about fraud detection ERP systems, and this was something that I was doing extensively when I was working for PwC, for example, what we did was, we engineered a lot of so-called handcrafted features. For example, we searched the ERP transactions for unusual ratios, for example, or for certain probabilities in single dimensions. For example, rarely used user accounts, or for example, if there was maybe a more complex pattern like the vendor bank account changes of a particular vendor has been changed, then a payment was generated, and then they have been changed back. So these are all these rule-based or handcrafted features, right, that we then could use and feed it into a classifier, for example, to predict if a certain transaction is fraudulent or journal entry is fraudulent or not. In the end-to-end learning approach, and this is exactly what you said, is we, to a certain extent, want to get, and I'm always emphasizing to a certain extent, we want to get rid of this. We want to feed the raw journal entry data to our models, and the model should ultimately learn what is unusual in the data in comparison to all the ERP transactions or journal entries that we have in the system. But there's one flip side, and therefore it's great that after this presentation, we have the presentation of you, or Abigail, that in terms of explainable AI, one challenge that we have as humans, though, is still to a certain extent to understand what are the features that have been learned by this end-to-end learning approach. I mean, we can, to a certain extent, for example, in the image domain, nicely visualize this, like we see here with the edges. But if we think about more higher dimensional domains, or maybe more, if you want to say maybe complex domains, or especially also about ERP transactions, it might be not so easy to understand exactly, or for us humans, it might not be easy to understand exactly what is it that the system has learned without maybe adding some kind of explainability or XAI methods on top.
Yeah, makes sense. Thank you.
Does it make sense? Yeah. Okay, cool. Perfect.
I also have a question actually off of what you had just said. So like with traditional machine learning, I mean, obviously the more data you have, the better the model is, but you can still kind of create a model with as few as, let's say, like, I don't know, 100 data points. Is there sort of like a minimum number of data points that you would need to do something like deep learning, or?
That's a fantastic question, actually. Yeah. I think it really depends on the use case. So it's really tricky to answer this question in general. But in general, deep learning approaches are very, very data hungry. So it means that the more data you have, the better you can actually learn or train such a deep learning system. And the reason for that is actually based on the number of parameters. If you think about these deep neural networks, we have a huge volume of parameters that need to be fitted in order to learn such a model, right? And if we don't have a significant portion of data, and at the same time we have these very powerful models with a high number of parameters, there is this chance of easily overfitting to the training data, and therefore our model won't generalize anymore beyond the training data that we showed at the model as part of the training process. And therefore we need a lot of training instances. So usually if you think about maybe journal entries or ERP transactions, I mean, this is maybe more just my empirical assumption, but I would definitely not train such models maybe on a population of less than 10,000 journal entries.